Whatever. Okay, so I had a review. Where to go? All right, so I want to do a quick review, and this is an important piece of review. So we're going to review two big things right now. First, we're going to start with this. Arrays. Y'all remember arrays? What is the runtime to get the value at some index of an array? Constant time. Why? What do you think? So why can I get to just some arbitrary place in an array so quickly that I can't do it in a linked list? Who wants to tell me? Who wants to tell me why an array has constant time access, but other data structures do not? Why is it? Does nobody remember? Do you remember the analogy that I used with like the camera?
Yeah, the angle of it.
The angle of it?
Just plug a number and it goes to it.
Right, you know the number you need to go to. And why is that, right? Because there's something in your computer. Okay? So speak up. What's your name?
They have addresses. Say it again.
What's your name?
Brianna.
Brianna from Long Island says. It's true, isn't it?
It's true, not for long, but it's true.
Not for long. No worries, it's no judgment. Right, so you were saying the right shit. Keep going.
So the RAM they're split up, what is it, depending on however many gigs you have, determines how many black pieces that you have.
So you have like these physical RAM, which is like segmented into gigabytes of RAM. It's like a physical thing.
And they're basically like addresses.
Exactly, that's the perfect word. Not their basic address, they are addresses.
And then when you key into a specific one, it goes straight there. There's no figuring anything out, it just goes straight there.
Totally, so like basically you have this, so did everybody hear Brianna? No. You didn't hear Brianna. Who didn't hear Brianna? Brianna didn't tell that person. Who didn't hear?
What was it? It sounded like that too.
You didn't hear Brianna, say it again, she said it right. She said it right. Say it again. Louder.
So the RAM has addresses, so when you go to anything in an array, it goes straight to the address. There's nothing to figure out. It goes straight there.
Okay, so that last thing is only half true, right? So basically in RAM, your physical computer has RAM inside. RAM, you can say, hey, I want to go to RAM address 6,742. It gets there immediately because the physical hardware is built for constant time access of any address. And an array is a contiguous chunk of addresses. So if you know where it starts, and you know the index, you know the address because you just do the address of the start plus the index times the size of the element. So if it's numbers, it'll be like 32 bits at a time, or maybe 64 bits if they're big numbers. It could be arbitrary size structure, so it doesn't matter. Let's pretend that every address is of size 1, and each element in the array is size 1. So it's just the start of the array plus the index. And so if the array starts at 10,000, and you want to go to index 500, you go to address 10,500, there's your data. It's constant. Okay? The reason why this is important is because today we're going to learn a data structure that's also constant, but for a very, very different reason. Okay? But it will be built on top of this. Remember we talked about abstraction? Okay, anyway, so everyone knows that it's constant time, sort of nobody knows why, so let's definitely try and remember the why, because I feel like it's a lot easier to remember the what if you remember the why, but hey, if you remember the what without the why, it's fine. Okay, so now let's talk about linked lists. So if you want to do some linked list, at index or whatever, like that. What's the runtime of some linked list LL at index I? What's the runtime of that?
N.
Where N is what? The position, right? So if I is 0, you can actually get it at a constant time. But if I is like 1,000, it's going to take 1,000 steps to find it, right? So it's really big O of I, actually, right? Or big O of the index or transfer flow. And why is that? Why is it so much slower to access a value inside a linked list versus an array? Who wants to tell me why? Let's do somebody different. Yeah, over in the yellow.
Is it maybe because like on the array, it's like kind of spread out?
That's exactly right. So it's not contiguous in memory. So you don't just know where the 1000th element is. You just don't just know, oh, the 1000 elements is 1000 away from the start. Right? It could be anywhere. It's spread out, right? So how do you get to it? How do you get to the 1000th element? What do you do?
You have to connect each one to the next.
Yeah, all that alarm is telling you, yeah. Okay, what do you mean connect, though? What do you mean connect? Can you be a little more specific?
So, you start with like the head, then you connect that head to the next node.
What do you mean connect? What does that mean?
Link it.
So you, like, I guess what does it mean to link it? Like, are you performing assignment? Are you, what are you doing?
Basically transferring like information from like one node to the other.
You're transferring information from one node to the other. That sounds like assignment to me. You're assigning a value. No? What do you think? I'm not sure. I'm not following this. I think you might be having the right idea, but you're using maybe the wrong words. So, because you really shouldn't be, like when you transfer value, that means that you're changing the value, but you shouldn't be changing any value. What really you want to be doing is you want to be following pointers, right? You go to the head, and the head has a pointer to the next element. And you follow it. You say, okay, well, let's see where that pointer goes. And now I am looking at the next element. And it has a pointer to the next. I follow that pointer. Right? Is that maybe better or worse? Is that helpful or not helpful? Okay, well, how would you describe it, I guess? Like maybe if the word follow, you don't like it. What's a better word? It's not really transferring, right? It's really like you're finding clues, right? It's like you go, it's like a scavenger hunt. You go to the first place and it says, oh, the next element is in another castle. It's in castle 600. And you go to castle 600 and you open it, and it's like, oh, the next element is in castle 30. And you're like, okay, shit, I go to castle 30, and you open it. It's like a scavenger hunt.
So would it be like passing information?
Well, I guess I don't understand. Who are you passing information to?
Well, from like one this to the other.
I'm not sure I follow that. Because it's like imagine that your friend left a diamond for you, right? There's a diamond, you want this diamond. It's worth a lot of money. Don't you want it? Go and get it. So they left you an envelope. In that envelope is the address of a house where it's at. You go to that house, and in that house is an envelope. You open it, and there's no diamond. Instead, it says, sorry, the diamond is in the next house, which is really far away. It's in Connecticut. And you're like, okay, fine. And you go to Connecticut, and you find the house that you're looking for, and you go there, and there's no diamond there. There's an envelope, right? And you open that envelope, and it says, sorry, it's in Jersey. Right? So, like, are you transferring information? Is information being transferred? Like, no, right? You're reading envelopes, and those envelopes are telling you where to go. Right? It doesn't sound like transferring information.
It points to the location.
Yeah, it points to the location, right? It's like it's a new address, right? Brianna used the word address, and she's like, it's kind of like an address. It's definitely an address. And in fact, in C, when you're like C programming, what's a pointer? Right? It'll tell you like, oh, it is an address. That's like literally, no, I'm serious. Right? I'm not being like, oh, good job. It's like, no, actually, like in the programming textbook that teaches you like how to write a compiler to write machine code that runs on the CPU, they talk about the word address. And when you're writing like if you're writing Verilog, which is a language used to describe hardware, so you're trying to build a circuit that is like fits onto a motherboard, like a chip, and you want it to access RAM, you're going to use address. Like that's a really common word. So like that's not just an analogy. That's actually the word that we've chosen to use because it's such a strong analogy that we're like, okay, that's the official word. So a pointer is just a nice fancy name for an address, right? And so you open the envelope and there's an address in there. And then you go to that address and then you open the envelope there and that's an address. So I like the word following, right? Another word is to like go to the address. That's another way to think about it, right? But you have to go to each address because you don't know where the diamond is, right? You know that the diamond is at the 100th address. Okay, well, I have to look at the first address to find the second. I have to go to the second to find the third. I have to go to the third to find the fourth, Is everybody following that? Okay, that's a linked list. So I really want you to think about this address analogy and the like scavenger hunt analogy. Okay. All right. So we talked about arrays. We talked about linked lists, and I do not want you to, those two things need to stay in your head. Okay. Because we're about to learn a brand new thing, and it will be a combination of those two things that will create an abstraction that will be the greatest abstraction of all time. Okay, and I mean this with all honesty. It's the coolest shit. Why is this open? Okay, ready? It's called a hash table. Perhaps you've heard this before. Perhaps this will be the first time you've heard it. Either way, it's going to be great. Get excited. Okay? I'm going to stand up because I'm so stoked on this. All right, so what is it? Okay, sometimes people will call it a hash map. Sometimes they call it a hash table. Sometimes in JavaScript, they'll just call it an object. Those are all the same thing. I might use them interchangeably, and if it's confusing, I apologize. But they're the same thing. There is no difference between them. It's like an automobile and a car and a book. It's all the same thing, right? They're just different words for the same thing. Hash map, dictionary, that's another word. Associative array, those are just the names for a different thing, right? It's like a table, a dining room table, a coffee table. They're all freaking tables, right? So that's the same thing here. It is one of the most useful and commonly used data structures. This is absolutely true. One piece of advice that I give, and don't follow this advice 100%, but probably follow this advice like 99% of the time, is that if you're in an interview, and they're asking you a data structures question, and you're like, oh shit, I don't know. Just say hash table. You probably will get the right answer, right? Like you might fail the interview because they'll be like, good, right, then do it. And you'll be like, oh shit, I just did what Ben said, and I just did hash table. But actually you said the right thing. And so obviously that's not enough to get the job, but it's a good first step to know that like probably the right answer is gonna be a hash table. So my hope is with that story not to like be like, look, all you do is say hash table. My hope with that story is to inspire you to get excited about this lecture, and especially to be like, really invested in this because this tool will be your power tool, right? This is the power drill that you can fit all kinds of bits into to drill all kinds of holes into all kinds of walls and build anything you want with this shit. Okay, this is going to be the most powerful thing. I use these every single day. Every single day that I'm programming, I use hash tables, okay? All right, so let's say that you're a cashier and a customer asks you, hey, I've got this peach, it didn't have a sticker on it, I couldn't find the price tag in the produce place. How much is this peach? Right? What is the cost per pound of this peach? And if we had an array of prices, right, that were like, okay, we've got a book of prices, and they are, maybe they're in order by price, or maybe they're in order by how recently they were added to our catalog at the grocery store, or some arbitrary order. And you're like, well, I don't know, was peach added recently or later? Was it cheap or was it expensive? Was it peach season? I don't know, I'm new to this job. How long would it take for me to find the price of this peach? On average. What do you think? With the cool marble sticker on your, what do you think? No, you don't have a marble sticker, dude? Exactly. It's not a sticker. How long would it take? You have this book, like you're a cashier at this store, right? Someone comes to you with a peach, like how much is the peach? And the book is ordered by how recently this product was added to the product manifest at your store. And you don't know how recently it was. How long is it going to take for you to find the price? However big the book is, right? And so what's that called? That's called linear time, right? That's called linear time. You have to look through the whole book. On average, you'll look through half the book, right? Because it's just as likely to be in the first half as in the second half. So on average, it's about halfway through the book, right? Expected value, half the book, which is linear time, right? So that's exactly this problem here. Runtime would be O of n, right? O of n, where n is the size of the book here. So that kind of sucks, right? So what would be a really smart thing to do would be, I don't know, organize the book by, let's say, alphabetical, right? But if it's alphabetical, the computer isn't like very good at like finding something that's alphabetical. Like a human is like, oh, it's Z, I know that it's towards the end, right? But like a computer doesn't know, like, well, what if everything is Z, or very few things are Z? So the way a computer would do it is to do a logarithmic algorithm where it would look in the middle, and then it would know, oh, is it in the first half or the second half? So there are ways to do this problem, right? But wouldn't it be better if I could just be like, I just want to know the price of a peach, and I just ask the computer, hey, peach. And the computer's like, oh yeah, $2 for a peach. How much could a banana cost, right? You know, how much it says a peach is, it's not even here. They don't have peaches. So strawberries apparently are $2, but it's about a big box of strawberries. So what if we ordered it, right? So what if we ordered it? We ordered it, we could do binary search, right? Have you learned binary search? Okay, so I already just explained it, but I'm not going to explain it deeper because I don't want to confuse you. But it's really fun and awesome, fun algorithm that I'll teach you later. But basically, if it's alphabetical, you can find it, right? If you've ever looked for a word in the dictionary, you don't have to look through the whole dictionary, right? But it's still kind of slow, right? Like when you Google shit on the internet, it's fast. You Google peach, the first result is there, peach, right? But if you look in a book for peach, you're like, oh, you're looking for like pears and pineapple and persimmons. You're like, oh man, there's a lot of peas in here. Like, you're searching through. It's not instant, right? So we really need to optimize because you want your job as a cashier to not suck. It sucks to be a cashier. You're not getting any tips. You're looking through this book really slowly, right? So even if the book was organized alphabetically, it's still kind of slow, right? It's still kind of slow. So imagine if you could just ask your friend, and your friend just memorized it all, right? Your friend just memorized it. He's like, oh yeah, peach is $2. Oh yeah, apple's $1. Oh yeah, bananas $1. Blueberries, it's $1.96, right? And they just knew it, right? If they just knew it, then you could just ask your friend, what would be the runtime of that? Constant time, right? So let's build that data structure. Let's build a data structure that is the friend that will tell you in constant time some arbitrary fact, right? Like, what's the price of tea? What's the price of peach or whatever? And so how does that work, right? So that thing is called the hash table. So the way that it works, there's going to be 3 big pieces. We're going to start with kind of the last piece, and we're going to work backwards. We'll start with the first piece and work forwards, but really in mind, ultimately, you'll see that the last piece is what really brings it all together. This first piece is, there exists a hash function, okay? What is a hash function? A hash function is whatever you want it to be, actually. It's a subjective choice. There exist good hash functions. There exist bad hash functions. But fundamentally, a hash function has 2 important features. It is constant time. It is consistent. Okay? And when I say those 2 things, there's no trick to what I'm saying. I'm not saying like consistent, what does that mean? Like, hey, when you're reading a book, you're like, well, consistent has all these different meanings. Like, no. Consistent just means when you run the hash function on peach, it gives you the same thing every time. Every time. If I say, hey, what's the hash function for peach? It's like 10. And I'm like, hey, what's the hash function for pear? It's like 50. Oh, what's the hash function for peach? What is it? 10. It's 10, right? Some other hash function might exist where peach is not 10, it's 78. But in that hash function, as long as it's consistent with itself, peach is always 78 in that hash function, and peach is always 10 in this hash function, both hash functions are both fine. They don't need to do the same thing as each other, but they need to do the same thing as themselves. If some hash function says, hey, what's peach 10? Hey, what's peach 11? That's not consistent. That's broken. It doesn't work. It's not a hash function. Okay? So what are the 2 features of a hash function? They are and constant, right? Okay. So what can a computer do in constant time besides an array lookup? Because we talked about that already today. What's another thing that a computer can do in constant time? What are computers really good at?
Math.
Say it loud.
Math.
Math! Computers are good at math, right? Computers can multiply numbers really quickly. They can add numbers, they can subtract numbers, they can divide numbers, they can perform modulus. Remember, you guys have learned modulus? Right? Modulus is just division, but it's the remainder piece. That will be really important very soon, but I'm not just yet. But fundamentally, what was your name? What was that? Jonathan?
Yeah.
Thank you, Jonathan. Fundamentally, what Jonathan said is absolutely key here. Computers are fast at math. And they are fast at complicated math. They can multiply 16,975,442 by 782,972 divided by 6,802 in constant time. And it's like, you're like, what were all those numbers? Computer's like, I don't even know. I did all of that stuff in less time than it took to render a single pixel on the screen. And it's doing this 60 times a second, right? Computers are extremely good at math, okay? So a hash function can just take something, do some math on it, and that is going to be constant time. As long as that math isn't like some function of the size of the input. Usually it isn't. Usually it's like, I mean, it can, but anyway. It does math in constant time, okay? So let's get rid of strawberry and blueberry for simplicity's sake, and we're going to, it's weird that this is a quote, but, and we're just going to have 3 elements. So we're just going to do apple, orange, and banana. So forget about peach, I apologize. And we're going to say, let's say apple maps to 4, and orange maps to 2, and banana maps to 7. So that just means like there exists some math function, right, that takes like the letter A, and the letter P, and the letter P, and the letter L, and the letter E, and it like adds them all up and divides them by 10 and multiplies them by each other. It doesn't matter what it is, right? It just matters that that function always does the same thing for apple, and it will do the same thing for orange, and hopefully have orange have a different number. So we talked about there's 2 things that a hash function has to be. It has to be consistent, and it has to be constant time. But it should be extremely diverse. And what I mean by diverse, it means that 2 things, like 2 different things that go into the hash function, should have a value that's extremely different. You want the values that the hash function does to be of extremely large range and extremely different. So like apple and apples, apple might be 10, and apples might be 600,782, 479, 672,489, right? Some like huge number that's totally different. Even though apple and apples seem really similar, the hash function is going to be really different. That's the sign of a good hash function, okay? And we'll see why that is. So now we're going to get to the money here. Okay, so I'm not going to read this thing. I'm going to do a little whiteboarding. Is there a pen? Can I use this one? Okay. So, do you remember how we've made arrays? And do you remember when we talked about how arrays have this amazing feature because they're contiguous in memory? That if I have some index, I can go to the element of that index in constant time. So imagine that I hash, what am I hashing? Apple. So this thing is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? So apple is going to map to 4, and orange is going to map to 2, and banana is going to map, what is it, to 7, okay? So what I can do is I can say, all right, well, apple maps to 4. I'm going to put apple right here. And orange maps to 2. Okay, I'm going to put orange right here. And banana maps to 7. Okay, cool. I'm going to put banana right here. Okay? Pretty straightforward, right? I take this string. I perform the hash function, which is constant time and always the same. And it gives me 4. And I go to index 4 of my array and I put apple there. Right? And maybe instead of just putting apple there, I put apple and I put some value, how much it costs. It's like $1. And orange is $2. And banana is, $1.50. And then later, when someone comes to me and says, hey, how much is an apple? I do the hash function, 4. I go to 4. I see the apple's there, $1. Constant time. Question?
So like the hash code is kind of like an index?
Hash code is exactly an index. So far. It'll get a little bit more complicated. Like right now, I'm starting you slow. This is like training wheels on the bicycle. You're not yet riding a bicycle, but you're seeing the pedals turn, you're seeing the wheels turn. So right now, yeah, not only is it sort of like an index, it's exactly an index. I'm just using the hash function to get some index for that value. Because what is the index of Apple? I don't know. The hash function is a way to get the index. Okay? Any questions? It's a good question. Any other questions? What? Through the hash function. Right? Apple hash function returns 4. Right? A function is a box. You've written functions before, right? Functions take inputs, they can return outputs. Hash functions are a specific kind of function that take an input, return an output, and they always return the same output for the same input. They do it in constant time, and the output is a number. I guess maybe I should mention that. The output's a number. Okay? That number, we're going to use it as an index. Okay? So let me, just because, what was your name with the colorful hat? Cue ball?
Cue ball.
I'm sorry, say it again.
Cue ball.
Oh, cue ball. Right. I remember you doing it last time. I'm sorry, you were sitting in a place, and I forgot. I don't know. I'm bad at names. You all have to sit in the same spot forever, so otherwise I'll wish. I wish. Oh, is this drama?
Step out of this.
Okay, alright. Paul asked a question. So it's just an index, right? Definitely. But what if, remember how I talked about to make a good hash function, you want the outputs to be a really wide range, right? So let's say that the range of the numbers coming out of this hash function is 2 to the 32. Okay? So 2 to the 32 is a pretty big range, right? 2 to the 30 is a billion. 2 to the 32 is about 4 billion. So it could be any number between 0 and 4 billion. So these numbers are obviously not between 0 and 4 billion, they're like between 0 and 10. So what if apple's 4 and orange is 7, but banana is 706? Where do I put it on the array? Where do I put it? Okay.
Would you like find the power of one of these indexes and just kind of have some kind of like 3-dimensional index? Like, I don't know, like, I don't know the actual math, but like,
just invented something way smarter than anything I've ever heard of.
let's just say like 703 is like, I don't know, 3 to the power whatever.
706 is just some random number I came up with.
Yeah, well, like, what if it was like 3 to the power of something is 706? You know what I'm trying to say? That way you only have to use like 0 through 9 and you just give it a power to get that number.
You're on the right track, but I'm going to go with no.
Okay.
But you're on the right track, right? You're thinking about like, what math could I use? But I don't know exactly what math you're talking about, and maybe it's really smart and I'm just not smart enough to understand it.
Okay.
But I don't understand that, sorry. But you're on the right track, so let's all think about this. What math could we use to consistently place banana in an index? And you're going to hear this, I'm going to say index, but I'm going to start using the word bucket. And when I say bucket, what I mean is this array has a bunch of indices. Each thing at this index is a bucket. And it's a new word, and it's, you might be like, why don't you say index? Well, you'll see in the future that a hash table is a little bit more complicated. Like I said, it's training wheels slowly, right? You'll see it's a little bit more complicated, and so a bucket refers to a specific kind of array with a specific kind of thing at the index, and that thing is a bucket. And you'll see why that is. But for now, think about a bucket as the thing at the index, but not for all arrays, just for hash table arrays. Okay, I thought I saw a hand up. Yeah, in front, right? Let's see. Oh,
You have more than one. Well,
okay, you're about to ask an amazing question. Just hang on to it for a second. Because instead what I want to hear is, how do I figure out where to put banana if banana is 706? If the hash value for banana is 706, how do I figure out where to put it?
so would you be able to use modulo and then whatever the remainder is, then you put it into the thing?
Did everybody hear Brianna? Super smart Brianna in the front row who's been just knocking them down every day. Say it really loud so everyone can hear.
So if you use modulo, you get the remainder, and that the remainder is always going to be the same, which means you can have a consistent number as the output.
So the index, so the bucket index is equal to the hash function of your element, right, of the thing you're hashing, modulo what?
Right.
The length. Oh my God, you're killing it. The length of the array. I think in JavaScript it's array dot length, right?
I'll do that common for mathematics.
Array dot length. Can you read that? Sorry, it's a little bit. Okay, I'm going to stop calling her Brownie because she's way too smart, and I want everybody else to catch up to her. So this is exactly right. This is it. This is key. This will never be. This is not. We're taking the training wheels off slowly but surely. This is now the real deal. The bucket index, right? The index in the underlying array, which we're going to call the bucket index, so hash map, hash table, object, dictionary, all the same. When you want to say, hey, which bucket do I put it in? Which index do I put it in? You take the hash, you modulo it by the length of that array. The array can change lengths, and we'll see that in the future, right? Because when you put a lot of things into an object, you'll need a longer array. And you put just a few things in an object, it'll be a shorter array. Fewer things in a hash map, it'll be shorter. And so this array.length is a variable value. It's not always like, oh, well, I'm going to use array length 10. It's like, well, I might change the length of the array in the middle of the hash map, and we'll see what that looks like. So this is key right here. The element hash function modulo the length of the array gives you the index. Why is that? Okay, there's two things. One is modulo is extremely fast. Computer can do it in constant time, right? You can do the hash in constant time. You can do the modulo in constant time. It can look at the length of the array, obviously in constant time. And then it can take that number and go to the index. How fast? Constant time. So far, every operation is constant time. So we're trying to build, remember we're trying to build this friend who's going to help you at the grocery store. You're like, hey, how much is a peach? She's going to tell you right away, right? And everything that she does has to be constant time. If she does a single thing that's not constant time, we're fucked, right? Because if she's like, oh, I can do this account, I can do this account, and then I need to look it up in a book and it takes linear time, well, the whole thing takes linear time, right? You're only going to be as fast as your slowest operation, right? Are we following so far? Do you want to like ask me questions? Yeah, questions.
That last part, but the element, the hash element modulo, the array.length equals
the bucket index.
the
The bucket index is equal to the hash function of the thing that you want to put in the object, in the dictionary, the hash of that element, modulo the array.length, right? And so what is modulo, right? Modulo is remainder, right? So when you divide something, when I divide something by 10, right? The remainder can't be 11, right? Because if something has remainder 11, actually has remainder 1, and it's just 1 bigger, right? Like if I'm like 21 divided by 10, right? The remainder is, it's 21 divided by 10 is 2 remainder 1, right? So what's really neat about modulo, and like honestly, I don't know shit about remainder. I know a lot about modulo because I'm not good at math, I'm good at programming. And programming, because of some kind of cool coincidence, fluke or whatever, tells me that the range of values that a modulo can have, that a remainder can have, is 0 to the number that I'm dividing by, right? I can't possibly have a remainder 10 or greater if I'm dividing by 10, right? And that's just like a fact. It's not, there's no magic there. Right? You should maybe test it out, prove it on yourself. Maybe you'll break it into groups and we'll talk about it in a second. But why we use modulo, right? So you can write this down, you can memorize it. But for me, what's helpful for me to remember it is I remember modulo because I know when I modulo something, it means I'm going to get a number back, which is between 0 and that number. It will be including 0 and not including that number, right? Like, if I do modulo 11, it could be 0, it could be 1, it could be 2, it could be 3, 4, 5, 6, 7, 8, 9, 10, but it can't be 11. So when I think about modulo, I don't think about remainder because I suck at math. When I think about modulo, I think about a loop of length, the thing that I'm modulating. I'm doing modulo 100. It's a 100-step loop. Starting at 0, all the way up to 99, and then when I hit 100, I go back to 0. And that's what we're doing here with this array, right? Like banana is 706. Really, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Follow what I'm doing here? And eventually I'll get to 706. And it'll be like, oh, sweet, it's here, right? And wherever that is, and you'll see that it's, I don't know what it is. Well, it'll tell us, it'll be like, whoops, don't read my history. Oh, God. What was it? Was it bad? I try not to. It's my work computer, you know. 706 modulo, was it 9 or something?
Yeah,
9. So we'll see. Oh, man, so it's 4. Why did that make me do 10? So it's 4. So it's going to go right here where Apple went. Okay? So I bet you there's about to be a question. Wait, the apple's already there. You have a question?
Well, I was just thinking, like, does it count the layers that it goes through, something like that? Like, this is 0 through 8, 1, this is 0 through 8, 2, like, to count like that, and then it knows that it's for whatever number.
Right. So you don't need to count layers because you can do it in constant time. When you
Yeah, it already knows.
Yeah, it's just division, right? So the number of times that it's looping is hash file length divided by read out length. Right? That's how many times it loops. And then hash element modulo read out length is how many times, once it's done looping that many times, it goes there. But you don't need to loop, right? That's kind of the beauty of it. It's like you don't need to go through each element. You can just do the math instantly, right? In the same way that a array, if you know where it starts and you know the index, you can just go there instantly. You don't need to go plus, like when I'm adding 100 to 10, I don't go like 11, 12, 13. I just go, oh, 100 plus 10 is 110, right? And so computer's the same way. It doesn't know how many times it loops. It just says, oh, I can just do this operation in constant time. And the point is that it knows exactly the index, and that's the answer. That's the index. End of story. It doesn't matter how many times it loops, because that doesn't provide us any useful information.
Right.
Or maybe what you were going to say is, we could use that information to handle collisions, to which I say, no, sorry. That's not. Okay, so let's take a deep breath, because I don't want to like overwhelm you. This is the shit right here, okay? And we're getting into it. I'm about to take the last training wheel off, and you're about to be riding free on this freaking bicycle. And then I'm going to take the front wheel off, and you got to unicycle. I know, it's going to be tough. But I want to make sure that we are okay with this, with the half of the training wheels off, okay? We talked about the array. We know the array's got constant time index lookup. We talk about the hash function. We know it's consistent and it's constant time, right? It just doesn't matter how it's implemented. We'll learn about that later. Right now, you just got to trust me that there exists a box that you can write, anyone can write, that takes in whatever you want, strings, numbers, objects, whatever the hell you want. And it comes out with some giant-ass number that's super freaking random, but it's always the same for the same input, consistent. And then you modulo with the array.length to see what index you go to, and you can go to that index in constant time. Everything so far, constant time. So far, we have now come up with a way to take like a string, like the name of a plant or animal or a fruit or a vegetable or whatever you want, and find its location in constant time in some array. But we've hit a problem, right? We've hit a problem. And that problem is, what if two elements map to the same bucket? And there's a word for that. It's called a collision. Okay? So, deep breath. And ask me any questions before we move on, because the next step's a doozy. Are there any questions? What questions do you have?
Just to clarify, we're talking about it. If that's the first bucket, it hits 4 twice, not 4 and then 7. Hashtag 4 and hashtag. Sorry.
So Apple's hash value is 4.
Yeah.
So 4 modulo array.length is just 4.
So we're talking about Apple's 4 and Banana's 703 colliding.
Banana's 706. 706 modulo array.length is 4.
So they collide even though 706 is 706 and 4 is 4.
Exactly.
Okay.
They collide because it doesn't matter that 706 and 4 are the same. it matters that 706 mod array.length is the same as 4 mod array.length.
So it doesn't know that it's in a higher level. It just thinks it's
What
in.
does that mean, higher level? Like, that stuff doesn't
Because
matter.
I'm visualizing it as like it starts off there, but then there's like an imaginary another bucket above
But
it.
there's no, but
Is
this
this
is
one
not your
bucket?
imagination. This is an array. This is an array in memory, dude.
Okay.
And remember why arrays are so fast? Because they're actually in your fucking computer,
Right.
right? So there's nothing imaginary going here. There is a physical array in your computer, which is contiguous RAM, right? And so this is like here is your RAM, right? Your RAM extends all the way over here, and your RAM extends all the way over here. And this piece of memory right here, this contiguous piece of memory, your computer has said, oh, I'm going to create an array of length 9, and I'm going to use it for this hash table, right? And so it doesn't have anywhere to store any of this other imaginary information, right? There is nothing imaginary going on. It just says, I have 9 indices that I can map to. I know where it starts, so I know that I can find it in constant time. And when someone gives me an element, I know how to do the hash function because I'm a program. I know how to do addition, subtraction. I know how to do some function that you gave me. I can call that function. I can perform modulo. I know how long the array is because I know that it's length 9. It's like something an array knows how long it is. And I can do, okay, this thing modulo that equals the index in this array. And now there are 2 things that go to this index.
So it makes another array inside of that index.
It does.
Okay.
Ooh, okay. Does it make another array? Actually, that's a really good suggestion, right? So I was going to say let's just pause half a second on that before we move on to like how do we handle collisions? Because I was going to say this is the doozy step. This is a big doozy step right here. Before we go on, are there any questions like about without collisions, just everything else we've talked to, not including collisions? Question right here.
Is this like JavaScript?
JavaScript objects are hash maps. Yes, they are. Another question over here.
So you're saying we have 9 buckets in this example.
Yes.
And we're able to hold more than 9 elements by process of whatever you're about to teach.
Yes. Yes. However, spoiler alert or whatever, you'll notice that this thing is sparse. This thing only has 3 elements in it, and it still has a collision. This is a very important trade-off with hash tables. Hash tables are generally very sparse. Not every bucket has an element. Some buckets have 2 elements, right? And that's because luck of the draw. That's because whatever the random ass output of these hash functions, modulo the length, it just so happens that everything maps to one bucket and nothing maps to the other, right? And that's a part of the law of large numbers. Like there is a chance that they map nicely. There's a chance that they all map to the same bucket. Okay, but yeah, you can fit more than 9 things in a hash map which is backed by an array of size 9. But actually, you often never do that. You always make the array bigger than the number of elements you want to put in there, and we'll find out about that later. That's a little bit of a more advanced topic. We haven't gotten there yet. I want to hear questions about the hash map, the hash function, the modulo, the bucket, everything up to the collision.
Full questions. So, are you saying the bucket can only be 9, or could we make it a little bit bigger?
We can make it bigger, yeah.
Up to like
This one happens to be 9 here.
So we can make it like 100 if we wanted to.
Make it 100, yeah. In fact, you will see and we will learn that they grow and shrink in real time. Question?
What kind of keys are that example?
Anything. Anything that can have all the keys are anything that has a hash function, and the values are anything at all. Even functions, sure. You can put functions in a hash map. Mm-hmm. Questions now?
So like, WAP always have 4, that always be the hash code that goes to Apple.
Yeah, Apple's hash code, Apple's hash, when you call hash on Apple, it returns 4. And because hash functions are consistent, and it's not that like Apple's always 4, it's that this hash function returns 4 for Apple. And you just always use the same hash function. So like, for example, Java has a different hash function than JavaScript, but always in Java, it's always the same, right? And always in JavaScript, it's always the same. And you could write your own hash function, and it would work fine, but you would need to always use the same hash function on your hash tables, and your neighbor could use a different hash function. As long as she used the same hash function on all her hash tables, everything would work fine, but you can't like cross-pollinate. You can't use your hash function in her tables. Everything would break, right? Because I would look for Apple at 4, but in yours it's at 6. And I'd be like, oh, Apple's not in this hash table. But it is, right? And then it would be like asking your friend at the grocery store, how much is an apple? And she's like, oh, I don't have apples here. And you're like, yeah, you do. You definitely have apples. I'm holding it right now. And it's like, well, because you're using the wrong hash function, right? You got to use the same hash function because that's the way that you could say, hey, I know exactly where Apple is in this place because I know that it's 4 mod the length of the array. Question on the side.
So basically, a hash function is something like it takes an input and then computes the address.
Yeah. Yeah, it takes a key, an input, sure. But yeah, it takes the thing that you're trying to hash, and it computes a hash value. It's not the address; it's a hash value.
That leads to
and then so with a hash value, you take the hash value, you modulo by the length of the array, right? And that gives you the index. And then you take the start of the array plus the index, and that's the address.
But because it's all like computation, that's why it's constant.
Yeah, everything that we said is constant. The hash function is constant. The modulo is constant. The array.length is constant. The finding an element within an array given an index is constant. Right? So far, show me the lie. Where's the lie?
No, that, like Apple would be converted into like some sort of math.
Yeah. Constant. Computers are really good at math, Jonathan said. Right, that's the name?
Yeah.
John, you have a question?
So during the event of the collision, do we create a multi-dimensional array?
Okay, so we're moving ahead. So there's no more questions. We're ready to do collisions. Okay? Ready to do collisions. I got you. Oh, we have a question in the back.
So, can you tell me again why it's necessary to have empty spaces between?
Okay, why is it necessary? Well, it's not necessary. Necessary means that, like, oh, if we don't do it, something will do it. But it's an emergent property of this thing that we generated, right? We have designed the system, right? We're making a system because the whole point of this is to be like, I work at a grocery store, I need this friend to tell me the price of peaches quickly, right? So I'm telling you, I'm designing the system for you. I'm helping you together through these questions in this conversation. We're going to design the coolest thing that's ever existed in computer programming, the hash table, right? And the way that we design it is we're utilizing a lot of these constant time operations. And in doing so, we use this math, we use this math, we use this math, we use the fact that we can go to an index in constant time to quickly define, to quickly decide, oh, I know where orange is, I know where apple is, I know where banana is. Because of all of these choices that we've made, that means that maybe nothing ever goes in bucket 5. Maybe there does not exist an element at your grocery store whose hash table, whose hash value, rather, right? The hash function of sour grapes or whatever, or a Sour Patch Kids or whatever it is that you're trying to find. There's just nothing in your grocery store has a hash value that modulo the array length is equal to 6, right? So it's not necessary that nothing goes 6. It just so happens to be that nothing lives in bucket 6. And in fact, what you'll find is that hash functions, or hash tables, the optimal size for a hash table is about 75% full. It depends on certain implementation details, but generally, as soon as your hash table has more than 75% of their buckets have a value, it's too big, and you'll make it bigger instead. Question in the back.
I think I might have answered my question, but is that why we're randomly picking numbers and not just like putting it in the next available space?
So, no, we're not randomly picking numbers.
I thought you said before the 706.
Well, it's not, so it's not random, right? It's consistent, right? And it's constant. It's not random. It's I guess, maybe I misspoke. If I said random, I apologize, I misspoke. Random implies that it's different every time, right? You roll the dice twice, you're not going to get the same thing. You might, but you probably won't. This is not random because it's always the same. It's consistent. But it's, well, maybe another word is it's arbitrary.
Right, you just pick that number.
Yeah.
And once you picked it, it stayed that.
Yeah, exactly. And you don't want to pick it like in a way where it's like, well, I just pick some number and then I'll make sure I pick the same one next time. You instead want to be like, hey, take this letter. Let's say A is equal to 1, and B is equal to 2, and C is equal to 3, and D is equal to 4, right? So take this letter and multiply it by 1, and then take this letter, multiply it by 26, and take this letter by multiply it by 26 squared, and take this letter, multiply it by 26 cubed, take this letter, multiply it by 26 to the 4th. Sum those all together, modulo by some prime number. That's like a huge ass number that's bounded by 2 to the 32. That is going to, that's an example of a hash function, right? It's like it just very quickly does some math. That will always be the same math. That'll be some large arbitrary number. More questions?
Are we able to look at data in more than one direction? Like if, how we're doing it, we're putting in like an index 4 for Apple and we get, we're putting in Apple and we get bucket 4.
Yeah.
Could we look at bucket 4 and get Apple?
But how would we know, why would we be looking at bucket 4? It's like imagine you've got your friend at the grocery store, right? And she's this like incredible machine who's going to tell you the price of everything. And you're like, I don't know the price of this pen. I don't know the price of the Coke can. I don't know the price of a MacBook. She knows it, blank, 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 right? And then you're like, okay, how do you know it? She's like, well, I have this really nifty like book where when you tell me the price of a thing, I add up all the numbers of the letters together, and I get a number, and I perform modulus on it, and then I know what page of the book it is, and I go to that page, and I read the answer. And you're like, okay, what's on page 17? And she's like, okay, on page 17 is Coke, Essentia water, and chips. And you're like, how is that helping you? Like, what problem did you solve by reading page 17 of the book? Just bullshit is on there, some random shit.
How to figure out what's in the box?
Yeah, but like, sure, but I'm telling you how to figure out what's in the box because I'm teaching you how the book is written. You understand? Like, you could do that, but there's, I think the challenge I ask you is, when you understand this, which it sounds like you do, maybe you don't, I don't know, but when you understand this, what value, what problem are you solving by saying, hey, what's that bucket 5? Let's see what's in there. What problem are you solving? How are you making your life better? How are you making the cashiers at the grocery store more efficient? What are you doing? What are you doing for them? And I bet your answer is going to be like, oh, nothing. It's useless, right? It's like you're reading a book upside down and backwards. You can get the letters, sure, but it's not going to tell you anything interesting. Okay, I think we've got enough questions. We're going to talk about, so the two of y'all basically gave an answer that's really interesting. What was your name?
Hammer.
Hammer?
Cameron.
Cameron.
Yes.
And Jonathan. I don't know. You seem like a hammer. I don't know.
I see some shorts.
Too much. MC Hammer? No. So, okay, you mentioned, like, oh, should it be an array of arrays? So why don't we talk about that a little bit?
Yeah.
Okay, so now we're talking about how do we handle collisions?
Well,
right?
I have like an image in my head.
Tell us about your image in your head.
Well, if two things collide, they generally go upward or downward.
Okay.
Depending on gravity. So, like, just kind of stacking things up.
Okay. Sure.
Or reverse.
But this is in the computer, right?
Yeah.
So there is no up or down, right? There's only left and right, right? There's only left and right on the computer, right? Because memory is a single address space. So when I have these like pointers up and down, really what this is saying that, oh, there's some address here, right? There's some address here. So I go to bucket 4 to find Apple, and what's there is actually the address of somewhere else in memory, right? Just like a linked list. Remember how a linked list was like an envelope with the address of some other building? So this array has in it, it says like, oh, it's going to tell me the price of the peach or whatever. So I go to bucket 4, and what's there is actually an envelope with an address. And that envelope says, oh, okay, I go to that address, and there is, written on the plaque of that address, peach, $1.
That's not the same, right? Because that's linear, wouldn't it be? And you're
No, because there's only
constant.
one address. There's only one address.
What are those 4 million addresses in that for?
Well, how could there be 4 million addresses in this box? This box only fits one address.
Well,
right?
they're trying to go there.
You can't put more than one thing inside of an
So it
array.
has to go somewhere, right?
You can only put, like an array can only have one thing in it at each element, right? You can't. Have you ever written an array in JavaScript that has 4 things in a single element?
Yeah.
How did you do it?
I mean, you have an array and you just make an object
Okay, so you had one thing, an object,
that has more.
right? Or you had one thing, an array. You can only have one thing in each element of an array, right? That thing can be big, though. What that means is that you go to that element of the array, there's an envelope, which is a pointer, you open it, and it tells you the address of a house, and you go to that house, and that house has lots of shit, right? So that's constant time to go to that house, right? It takes a while to go to a house, but it's only one house, so it's constant time. But how do we handle when both Apple, which is going to be $1, and banana, which is going to be, let's say, $1.99 or whatever? How do we handle when both of them map to the same bucket? What do we do?
Can they like combine into one value or one?
They can, but imagine if you asked your friend, like, how much is a peach? And she was like, banana $2, peach $2, and you're like, this is too much information. She like starts rattling off shit, right? She starts rattling off everything on the page, and you're like, whoa, whoa, whoa! I just want to know peach, right? And the thing about that that's extra is that in this situation you're a human. You can be like, whoa, whoa, slow down. But in this example, the computer is the one reading. Computers don't do that. Computers aren't like, whoa, whoa, whoa! I just want one value. Computers are like error. Unexpected type, right? Like you gave me an array and I expected an object. You gave me a string and I expected a number. Just error, crash, right? So what can we do? How can we design this? Why don't you talk amongst yourselves? Talk to your neighbors. Let's do a little group activity. Everybody likes group activities. Let's do a little 5 minutes. We can even do a 5-minute break plus talk to your neighbor for 5 minutes. We need 10 minutes. How are we going to do this? How are we going to make this hash map handle collisions? Let's go.
So we were thinking like, I feel like this is the way. Like we have your bucket, which is core, and then inside that bucket we have objects, and inside that object we have all the different values and elements.
You know, an object is just a hash, right?
Is this what? Is this a hash?
Yeah.
So is it
You're
reverse?
solving the problem with itself. So, what if
like
the
this.
collision inside this object?
So each bucket is basically an object, and inside that.
Yeah, I'm telling you, these objects, if they're implemented in JavaScript, they're hash.
Oh. So
these keys would have the same collision. They collide again.
So
They
these,
collide again inside that object.
those are the objects. Right? Buckets.
It's like, you know that story of like, the world is on a turtle? The entire world is on a turtle. It's like ancient Mayan.
Yeah.
And someone says, what's that turtle on? It's falling. And the wise man says, the turtle's all the way down. And that's what this is the solution you're describing. You're describing the turtle's all the way down. You're saying, hey, when the hash map is conclusion, we're going to have a hash map down. It won't work because those two things that collide, they'll collide in that new hash map too. Because they're going to use the same hash map.
Right. So then, what is it?
What's the data structure that we learned about? What's the data structure that we learned about? It's very good at growing and shrinking inside. Alright, we're taking a 5-minute break, everybody. 5-minute break. Get up, stretch your legs, walk around. 5-minute break. Go.
I was for the round, and that's what the community.
It's probably take multiple classes. But like, there is a situation where you would imagine every single bucket has like 5 things on it. So go to a bucket and I have to look 1, 2, 3, 4, 5. It's slow, right? So it'd be better if on average, every single bucket has 1 or fewer things. Usually a bucket might have 2 or 3, but 2 or 3 is not that many. 2 or 3 is usually thousands beyond the slope. So you want this to happen fast. One is you have constant time. The collisions because you might be 7 or 6, I might be 4. And 76 and 4 are mine. 7 or 6 and 4 are mine. 20. So you won't buy it.
To get ready to go take a test and double fix I'm a horrible person. Right. That's okay. It was really fascinating. It's not a regular
There's some time out there, not in the fridge. Still working Pfizer or you did?
No, still there.
Oh, wow.
Stuck. Using something right now.
within the company? There's a lot of value you can add. What's up, I was just learning about Dutch background. Okay, so who has the answer? I gave you a lot of time to talk to your friends about it. What's the answer? A couple of you figured it out already. So, don't say it. God damn it. Okay, so what do you think? I guess raise your hand if during that time you were like just completely lost, or like I have no idea. We got one person is willing to admit they're lost. 2 people. Okay, so I want those of us who are totally lost to kind of walk us through where we're at, and I want to try and guide you to the linked list answer. Okay. I want to walk you there. Spoiler alert, I kind of told you these answers right at the beginning. I don't know if you remember I said, we're going to take arrays, we're going to take linked lists, and we're going to combine them together, right? I literally said that when we've been doing arrays, so hey, guessing linked lists would have been a pretty good guess. But okay, tell me, you're totally lost. Tell me, what so far, like, what do you understand? Walk me through your current understanding.
So we have a hash function.
Yeah, function out.
That we give our hash function anything.
Yep.
And it returns a number.
Hell yeah.
Then we use that equation, I guess.
Yep. So we take the hash function, we modulo it by the array length to decide what? What does this give us?
A number in which to put it in the array index.
An index, exactly. An index in which to put it into the array. We're going to call that the bucket index. Okay, so you got it.
And now it's completely lost.
Now you're lost. Okay, so I'm glad that you understood everything up into the question that I asked you before the break, because that's great. So you're not completely lost at all. You just didn't get the next step. Okay. So let's talk about it. I think a lot of you got it, but I'm going to walk those of you through who didn't yet get it. Basically, what we've been talking about so far is, like, I don't know if you remember, you've made arrays in JavaScript. JavaScript arrays are not computer science arrays, but there's some things about them that are analogous. And these are, again, this is a computer science array, right? Not a JavaScript array. But basically, at any given element of the array, it can only be one thing. That one thing can be big, it can be small, it can be a number, it can be another array somewhere else in memory. It could be a string. It could be all kinds of things, right? The thing that we are going to use, let me erase this thing at the bottom here, is a linked list. And the reason why we're going to use a linked list is because it has the properties that we want. And even though it has one property that we do not want, which is linear time search, we are going to account for that linear time search through some other fancy means. We're going to talk about that in a second. But before we talk about the linear time search problem, we're going to talk about why linked list is really good, right? Linked list is good because if we imagine that instead of at this element having apple, what was at this element was a linked list, right? Where the head of the linked list is apple, and the next pointer is banana. Right? So this is like a linked list with the next pointer and a value, right? Remember how we built a linked list last class? We had a value, each node had a value and a next, right? So each of these elements, so the buckets which have nothing will just be null, right? They don't have a next pointer, they have nothing. They have no node, it's just null there. And so you know, well, there's nothing at bucket 6. But at bucket 4, there's a node whose value is apple. We're like, well, bummer, we're looking for banana. So we go to the next node of that, and we look at its value, and we see its value is banana. We go, nice, we found banana. Right? So what's nice about it is 2 things. One, we can add elements very quickly. What is the runtime of adding an element to a linked list? Constant time. Remember, that's from last week. Adding an element to a linked list is constant time. You just go to the tail, and you say, tail.next is my new node. this dot tail equals the new node, right? And now you add a new element. That's at constant time. Removing an element from the tail, or even from the middle, will be constant time. Okay, it's not exactly constant time because it's actually linear time with respect to the length of the linked list. But let's assume, just in the interest of conversation, and I'll prove it to you soon. But for now, you're just going to assume this linked list is short. It's not going to be very long. So if something is big O of n, but n is never bigger than 3 or 4, then that's basically constant time, right? Because like 3n is the same as n, right? And n over 2 is the same as n. But when n is 2 or 3, it's just a little bit bigger than 1. And so a number that is small is effectively constant time. Even if it is, you have to check all the numbers, but it's like I only have to check all 3 or 4 of them. So we're going to eliminate the cost of the linear time feature of the linked list by keeping it short. Okay? So anyway, the question was, how do you handle collisions? And the answer is, instead of storing values, instead of storing the thing that you want to store inside your bucket, the reason why we call it a bucket is because what is a bucket is actually it's a linked list, right? So a bucket has lots of things in it, right? You don't just put one Lego in a bucket. You put a couple Legos in there. You put a couple toys in the bucket, right? That's why we like this word bucket, because it's more than just an array index. It's an array index which has a linked list at its destination, right? So that is the definition of a bucket. It's a name for a thing that we've already seen before, but it's a specific kind of thing, right? It's like a Camaro. It's a car. You've seen cars before. This is a specific kind of car, right? Any questions on this?
Is it better to have a longer array with shorter linked lists?
Yes.
Okay.
Absolutely, 100% yes.
Okay.
That's why, if you remember, I earlier was talking to somebody, I think you in the Jersey Shore shirt, was saying something about empty gaps, maybe I think it was you. And I was saying that there is an optimal load. Oh, it was you with the sweet beard, sorry. There's an optimal load, right? It's called a load factor. There's an optimal size, and it's about 70%. Sometimes it's 50, sometimes it's 80, but it's generally about like 2/3 full. And when it gets to more than 2/3 full, what you do is you make the array bigger. Because when you get to 2/3 full, on average, you now have at least a few linked lists of length greater than 2. And you basically never want your linked list to be of length greater than 2. It happens. But it happens so rarely that it's like it's just a freak accident. It's usually indicative of a bad hash function, which we will see an example of a bad hash function soon. Where if you have a bad hash function and you're hashing a lot of like, imagine that you're hashing the grades of students or whatever. And it's like, well, nobody is getting between 0 and 50 on the test. Everyone's getting between 50 and 100. And so if your hash function sucks, everyone is like over here and this part is all empty. And these linked lists are all long, and these linked lists are all empty. So that's bad, right? It's not nicely distributed. You want the butter to be spread nice and evenly along the bread. You don't want a lot of butter on one side and no butter on the other, right? And so that's defined by your good hash function, which creates big numbers that are widely arrayed across the number space, and using this modulo. So yeah, it's a great question. Do you want longer linked lists or larger arrays? And we always want larger arrays. But you don't want the array to be too big, because then you're going to put 10 things in your hash map, but your array is of size 1,000. That's the recipe for Google Chrome taking up all your RAM, right? No, seriously, right? That's a big factor. And in an interview, this is the kind of thing that we love to talk about in interviews. So like, okay, what's the space complexity of that? Well, what's the time complexity of that? And you'll make a trade-off. You'll say, well, I could use a map here, I could use a hash map, but I'm going to use a lot more RAM, right? Because I'm putting a lot of things in this hash map, and hash maps take up a lot more space than a linked list or an array, because an array is going to be contiguous. If you've got 100 elements, it's going to take 100 things in an array. But in a hash map, you've got 100 things, it's going to take an array of size 100 plus 100 linked list elements, right? And maybe the array is actually size 150, right? Because you want it to be about 70% full. So you're now taking up almost 250% of space as an array would. But you're getting constant time access, right? You don't have to look through every single peach, pear, plum in the book to find the price of the percent, right? You get this constant time. So you're trading off space for speed. Question?
Is that how Google search works?
Google search is built using this thing called MapReduce, which is a very complicated technology that I will be able to describe to you towards the end of this 10-month program. And it will involve hash maps, yes. There will be many hash maps. And there will be such large hash maps that they fit on entire computers, where these buckets are so big that this is an entire computer with a terabyte hard drive on it. And you do this same thing. You do a hash, you do a modulo, but instead of modulo or 8-out length, you do modulo number of computers in my data center. And that's how Google works, right? So this concept is a huge concept that applies not just for little things in your computers, it applies for indexing the internet. And it's nested. It's a Russian nesting doll, right? Where it's like, oh, I've got these websites all mapped to that computer in the corner. And then in that computer, it says, okay, I'm going to break these websites up into another hash map, right? And so there's a lot of hash maps up and down the stack. Question again.
Are hash maps also scalable? If you need more, is it easier to scale?
No. Easy, no. Do they scale? Yeah. I mean, the thing is that you can't have a hash map whose size is bigger than the amount of memory you have in your computer, right? Just like you can have an array bigger than the amount of memory you have in your computer. So you need to be clever, right? And that's why Google can't fit the entire internet on one computer, right? So that's why it does a clever thing where it uses this thing called MapReduce, where it takes the website, it performs an operation on it to generate a bunch of metadata, and then it takes that metadata and uses hash functions to allocate arbitrary metadata to different machines in the data center, so that that machine is like, oh, I'm going to process every website that has the word Queens in it, right? And it's like, oh, how is that done? Well, we took Queens, we came up with some number, we took that number, we modulated it by the number of machines, and we said, oh, okay, look, we have 1,000 machines, Queens is going on machine box 33. And now box 33 now has all the websites, or at least some significant portion of the websites that have Queens on them, right? And so that's like a very, very cursory description of a much more complicated technology than that. But anyway, fundamentally, just to entice you, absolutely, this stuff that we're learning, it's not necessarily like a one-to-one of like what some of this like Google will be doing, but it's like, 1 to 1.1. It's like it's really close. And these skills are transferable. That's why I really want you to understand how it works. Because if I just say, hey, guess what? In JavaScript, there are objects. Objects are hash maps. They have constant time. Bye. Like that, you're not going to be able to answer these kinds of interesting questions. You're not going to be able to solve these kinds of interesting problems at scale when you're working at LinkedIn or Facebook or wherever you're working. You're going to be solving some big problems, and you're going to be like, oh, you know what? I should use a hash map to solve this problem because I know it's constant time. Or you know what? I should use the feature of hash maps. I'm not going to use a hash map, but I'm going to build my own system that allocates resources based on some consistent constant time function and a modulus on the number of buckets that I want to do. So like, you might use some pieces of this. Anyway, I love that question because it was exciting. Question?
So, is this the only way hash maps can pretend to be constant? Because it didn't look constant to me. It looks like it's pretending to be constant.
Well, it's constant with respect to the number of elements in.
Yeah, but
the
that's
only part of it that's not constant is this linked list traversal. Right?
That's a little disappointing. It's not constant.
It's not. And in fact, you haven't even learned the true disappointing feature. But I can prove to you that true disappointing feature is actually amortized out to a very happy place. But I haven't talked about it yet. But I don't want to teach you just yet because I feel like it's a lot to learn. We have half an hour left, and I want to talk more about what we've learned today. And specifically, I want to show you this hash function here. But it is constant time. Trust me on it. It is. And we'll talk about it more next time. We're going to do 2 sessions, just like we did in linked list. We did 2 sessions. We'll do 2 sessions on hash maps again as well. So definitely keep this all in your head forever, because this is going to be the thing that's going to get you a job. This class, I'm telling you. This particular class. Also, it's awesome. Any other questions before I talk about this hash function right here? You see this hash? So this is an example of a hash function, which it is indeed a hash function because it meets the three properties. I know earlier I said two, but there really is that third. It must return a number. But the three properties are it returns a number, it's consistent, and it's constant time. So this one is actually linear time with respect to the length of the key. But that's okay, because we can set the limit on the size of our keys, right? We can say, hey, keys can never be more than like 64 characters or something. Which is like a reasonable thing to say, right? It's to say, hey, no thing in our grocery store has a name more than 64 characters. And if it does, you can just truncate it. Because like the name is unique up to 60. You know, like there's not like two products in the grocery store that have different names, but the first 64 characters are the same. Right? And if there was, then we'd be like, okay, well, let's try 128 or whatever. But there is some bounds upon which we can make our keys, and therefore we can say it's still constant time because it's constant time with respect to, it's at the very most 128, right? Which is constant. Because even though something might feel linear, if it's never going to exceed some size, it actually is constant. It's just 128. It's a big constant. So this hash function, it's consistent, it's constant time, it returns a number. What does it do? It sums up the character code for each value. And the character code is just this ASCII table. It's just this ASCII chart. What is ASCII table? Have you seen this before? So there's a giant word salad here. Basically what it's saying Z is 122. Capital Z is 90. 8 is 56. The file separator is 28. Null is 0. The exclamation mark is 33. This is actually how strings are encoded in the computer. Right? So a string, when you say a string, it's actually just an array of numbers. And the computer says, oh, it's an array of numbers, but instead of just giving you numbers like 7, 22, 19, it's going to interpret those numbers as characters. And it's going to say, oh, the first number I see is 89, so it's Y. And the second number I see is 111, it's O. It's the string yo. Okay? So this is actually how strings work. Hopefully it doesn't blow your brain too much. And then what this is doing is it's adding up all of those numbers, and that's it. End of list. It just returns it. Okay? So why is this a good hash function? We've got some peeping toms over here. Do you have something that you want to tell?
I'm being nice.
A lot of peeps? I'm sorry. I apologize if I'm one of them. I'm trying to keep it. Okay. Why is this? What's good about this hash function? Somebody else. You raise your hand a lot, buddy. Let's do somebody else. Somebody else. Why don't we try you over here with the cool eyeballs on your laptop? That's you. That's you. What do you think? What makes this hash function good?
Is it because each index in the array has like just one element?
No, remember this hash function up here.
I don't know.
Wait, what question were you answering? What's going on? No, I'm saying this hash function right here, Blammo, right? It's a hash function. I'm sort of backpedaling. I wanted to give you the whole tamale. I wanted to give you the whole burrito. And then I wanted to just like take a step back and be like, all right, now let's talk about the rice. You know? Because the rice is key to a good burrito. And that's what we're talking about here, this hash function. We talked about it already, but I'm going back to it because I really want to, it's just the way that I chose to teach this class. What makes this hash function good? Somebody hit me with an answer. Somebody who hasn't raising their hand yet today. Somebody, what do you think? I feel like I remember it was like A. So it's an A? E? I don't remember what it is. It sounds like an A. Is it Alexis? Alessandra? I got it in the second try. Alessandra. But with an E. Alessandra.
Yeah.
Ooh, that's what I was mispronouncing it earlier. See? You learn something every day. Alessandra, what do you think? Why? Tell us why this is a good hash function. Or tell us why it's a bad one. Either way.
So basically, just adding up the number that each letter comes out with. So it's gonna be a unique number.
It's going to be a
Unique number.
It's going to be a unique number, and it's going to be the same for the same string, right? If I do Alessandra, and then later I try Alessandra again, it's going to be the same. Alessandra is never going to change what it returns from this function.
Yeah.
So that's good. But is it truly unique? You use the word unique. Is it truly unique? What's another word? Like, let's say we put in Alessandra, right? And we get back 1,000, whatever, 1,100, right? Could we put in another word that's also 1,100?
Yeah.
What would be another word that's also 1,100? Well, no. I think you would think of it. It's not a trick question. Look at that function. Look at that function and think about how could we break this function? How could we give it an input that would get the exact same output as some other input? What do you think?
This is the same, there's a different order.
You're a mean man. Thank you. Did you hear I mean? Use the same letters in a different order. This function is order invariant, which is actually a weakness, right? If I do Alessandra with an E at the end and an A at the beginning, or Alessandra with an E at the beginning and an A at the end, they'll get the same value even though those are different names, right? That kind of sucks. That's a weakness, right? I would much rather have a function that cares about the ordering, right? Because it's going to make it more diverse. Remember, diversity is a feature of hash functions. It must be consistent. It must be constant time. It must return a number. But it's better if it's diverse, right? So this passes our 3 requirements, but it fails our final check, our diversity check, because of what I'm saying. Is everybody following so far? So you can evaluate a hash function. And if you remember, this is why this is important, is because if everybody maps to the same hash value, they're all going to map to the same bucket, they're all going to go into one giant linked list, and you're no longer going to get a constant time performance of a hash table. Right? Question?
So you don't want it to be like dependent on like the order of the letters?
I do want it to be dependent on the order of the letters. Yeah. Well, the thing is, I want it to be as mixed up as possible. I want to make it so that it's really, really, really hard to get the same hash value for 2 inputs, unless those inputs are indeed the exact same sometimes. Right? If they are the exact same, then I want them to have the exact same value, right? Because it must be consistent, right? That's the definition of consistency. But if they're not the same, they better be different numbers. And ideally, they're wildly different numbers, right? Ideally, Alessandra gives me 1,000, and Alessandra gives me 16 billion, or whatever, right? Or I guess probably less than 4 billion. So 16,782,992. Make sense? I want it to be really, really, really different. And I think we can do... So there's lots of I guess there's probably SHA. So I want to show you this SHA-256. There's a lot of crazy stuff going on here. But so basically, remember how we talked about I want them to be fast. So in all the examples I'm going to give you, they're probably not going to be that fast because I don't want them to look like this has, right? This is ugly and hard to read. But the reason why it's ugly and hard to read is because computers are really good at math, and this is a way to use math to like mix up the bits, to be like, oh yeah, the string, all the sound, I'm just gonna like just shovel it all around really quickly and just like do some really quick math on the letters and get you a giantly weird number. So that's what this is doing. It's doing to the power of, it's doing a lot of like giant math. And it looks like a lot of code, but it's actually really fast. So check it out, ABC. This is the hash value for ABC. And if I do ACB, it's a completely different thing. And the reason why it's showing us these weird letters is because this is actually hexadecimal. Hexadecimal is just a 16-bit representation of a number. It's just a way to represent, you know how you can represent numbers in decimal? You represent them in binary. You can represent them in hexadecimal, which means we go 0 through 9, and then we also have 10, which is A, and B is 11, and C is 13, or it's 12, sorry, and D is 13, and E is 14, and F is 15, and then 16 is 1, 0. That's what, I don't want to confuse you. Let's just close this. This is too much.
Wait, no, it's not.
I'm going to leave that open so I need to look at your faces and learn your names. Anyway, so it's a hash function. So we got the answer. So here we go. So, question inside.
Earlier you said that Apple should be community of different numbers, right? Would you want it to be similar, like if you're because like, they're like the same?
Why? Why would we wait? Apple and what? Apple and banana are the same?
Apple and apples.
But they're not the same, dude.
Like I'm saying, like let's say you Google it, like wouldn't you want it to yield like the same results?
Okay, so you're saying, okay, so did you hear the question? The question was, hey, there's a semantic similarity between certain English words. Don't we want to have a data structure that can like model that semantic similarity? The answer is absolutely. This is not the data structure for that. This is a data structure for constant time lookup of exact matches, period. That's not to say that you might use this data structure. You know, remember how we learned about a stack and a queue? And those things are actually just built on top of a linked list? So you're going to learn about other data structures in the future, fancy pants data structures after you graduate. You're going to learn about some crazy fancy shit out there. And those things are going to be built with hash tables. But they're going to have nice features like semantic adjacency. But under the hood, what's going to be happening is it's going to have some semantic adjacency operation that will basically filter the semantics into some common language to be like, oh, perform this operation, this like non-math operation, probably some kind of logical operation, maybe even some human hand-coded operation, maybe even some lookups of some kind, to map values into a consistent value. And then it uses that consistent value as the hash key. But like this is like an advanced thing. It has nothing to do with hash tables. It has more to do with like, hey, I'm trying to solve some particular problem. I want to solve that problem about semantic adjacency. Well, how am I going to solve it? Well, we can talk about that problem when we get to it. For now, we're solving the problem of you're at a grocery store, you've got a friend, she's going to tell you instantly the price of goods, right? Let's focus on that. Question. What's your name? I was like, I thought it was Hammer, but
not Hammer. Hammer. There's one M in my name, yes, but
I remember Hammer, but I don't know.
There's one M.
It's really bad, man. It's really bad. I'm gonna get bad reviews on my next teacher. And he was like, he thought my name was Hammer. I'm really sorry, Cameron.
Yes. So to fix that, if you assign the number to each letter and then assign the number to each index, wouldn't you get a different?
Exactly. Right. You're talking about for this function.
Yeah.
If instead of just adding, what you did was you added this times I, right? You'd get something better, right?
Yeah, more unique.
Or even better, not times I, times 26 to the I. Because 26 is the number of possible characters that can be. Actually, it's actually 128, but think about it like you have a number, right? 732, right? And you're like, well, the 7 doesn't represent 7, it represents 700. And the 3 doesn't represent 3, it represents 30. And the 2 does represent 2.
Right.
So that's kind of the same with a string, right? You could be like Ben, B-E-N. The B doesn't represent B, it represents like, you know, B100. And the E doesn't represent E, it represents E10. And the N doesn't represent E. So like that's a way to think about But like, regardless, this is a fine hash function. It's not the best, but it's fine. Okay, so notice that our hash function returns the names. So Sally gives 517, Dean gives 376. Dane also gives 376, because like Armin said, they're the same letters in a different order. So what that means is that they're both going to map to the same place, and we're going to use this thing called chaining. Chaining is this linked list technology that I explained to you, okay? That's called chaining, where at the bucket is not a single item. The bucket is a chain of items, a linked list. Okay? There are other ways to solve this collision problem. I will only teach you the linked list today, and for the interest of like the next couple sessions, we'll see, maybe in the next session we'll branch out. But until I'm convinced that y'all understand this really well, we're going to just say that that's the only way to solve it. But just, I want to, spoiler alert, I'm teaching you something that later I'll be like, actually there are more solutions. There are tricycles, there are unicycles, etc. Okay? So, so let's implement a hash table. Let's do it. So here's a class, and we only have 15 minutes, but I would like you to break up into groups and implement all the functions of a hash table. Ready, set, go. I got some feedback. That was like, you didn't like the way that group selection went. So I'd like to know, how would you like me to do group selection? Because I'll do it however you want. I don't care. It doesn't matter to me. I just wanted to get it done with last time. Also, I was in a bad mood, so I apologize for that. But y'all really impressed me last time. That was one thing I wanted to say. Last week, I was like kind of grumpy. I had a really bad day, and I was like, "Fuck this! I'm just gonna make them break up into groups and do it." It turned out to be an amazing class, and everybody really, really, really impressed me because every single group got like really, really close to the answer, or even the one groups that like that had some bugs in their code, at least were like very, very much on the right track and thinking really critically about what matters. And it sparked really good conversations. I really loved last class. So I want to do that again. We only have 15 minutes left, so what I really would like to do is maybe break up into groups and remember your group. And then next week when we come in, those groups can present the same way presented last week, but you'll have obviously a whole week now to do it. Is that okay?
Yes, we have an assessment.
No, I mean, don't spend the whole week on this one function, please. But like, you know, and next week I'll give you like 10, 20 minutes at the beginning of class. How's that? Or you can tell Alejandro to give you 20 minutes before class to reconvene with your groups, get everything up on the whiteboard, and then we'll do the presentation. So let's spend the next 15 minutes doing that, and then I'll just peace out of here, and that's the end of class. How does that sound? So, so how do you want to do group selection?
How many functions are there?
Let's see. So there's insert, there's get. So let's do there's add, there's remove, and there's get value. So there's only 3. I think maybe we could do 6 groups. 2 groups do insert, 2 groups do remove, and 2 groups do get. How does that sound? Because I feel like 3 groups is that's too big of a group, right? So 6 groups feels better. Okay. So do you want to just self-organize? Do you want me to number you? Do you want me to like do it self-organize? Okay. I don't want any groups smaller than like 4 people though. Don't abandon anybody. Don't be rude. Okay. What's up? I did that, and I literally got feedback on the feedback sheet. I was like, I did not like this group selection strategy. I was like, it was random. That's true. Look, I'm telling you, put feedback that you like it, because if you don't put feedback, then
That's 30.
it's 30 in the class.
Pretty much.
6 times 5 sounds good. You got your math.
If you don't want to be
Okay, a lot of people are saying random. Does anybody that hates random speak now?
Dante, you hater. I feel like it gives you an opportunity to work with other people.
You want to do a poll? Want to do a poll on Slack or something?
Do you want to do raise your hand if you want it random?
Alright,
Raise your hand if you want it to be self-actualized, self-organized.
my
Just the 3 of them. Okay. The 3 of them get to be in a group. Everyone else on there do random. Okay? Alright, we good with that? Okay, so you're going to remember your number. Okay, so you're going to do 1. Okay, so your group number is 0. Okay? The 3 of you are group number 0. Okay, we're gonna go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. All right,
So nobody else is in 0 when
that's it. You made it to 3. Yeah, because you would have been 3, 4, 5, 6, right? It would have been perfect if this 3 of them would have been fucking. So,
Man, I got a monkey wrench. So now there's only 3 of us.
now you have a monkey.
I have a monkey wrench. We never annotated the 0. 0, and somebody goes
0, 0, 0. 1.
Yeah. We still need 5 people, right? We still need 5 people.
Yeah, but nobody else wanted to be in a group. And nobody said they wanted to be in a group. They said they want to be random.
Alright.
Lo siento. I think it's okay, right? No drama? It's okay. Yeah, I mean, feel free to, like, if you want to move groups, it's fine, whatever, it doesn't matter. What matters is I don't want any groups smaller than 3 people. Really smaller than 4, except for that group. That's the only group that can be as small as it is. Every group is at least 4 people. And I want to see a nice mix. Get in, mix it up. I like that you're mixing it up. And obviously, feel free to collaborate with the other groups. So I'd say, like, groups 1 and 2, can you do insert? Groups 2 and 3, can you do get? And groups 4, 1 and 2 do insert. 3 and 4 do get. And 5 and 6 do doing. Okay? And 0 can do whatever they want. Choose your own adventure. Let's have 1 and 2 should do insert. 3 and 4 should do get. And 5 and 6 should do doing. Does that make sense? Any questions on that? So it's going to be just like last time, except obviously you're going to start now. You've got 10 minutes. Let's just group up and start whiteboarding. And then at 10, take a picture of it. Remember your group, obviously. And then next week when class starts, I'll give you another 10 minutes or so to, like, rewrite it up and have a final conversation about it. You're going to choose a representative, and the 2 representatives, right, for each group, because there's going to be actually 2 plus maybe 1, right, 2 or 3 representatives from the groups that are like the insert, the get, and delete groups are going to then present the same way we did last time. I thought that worked really well.
Cool.
Does that all sound good? Yeah. All right, so meet up with your groups, and let me do some erasing so that you all have team space.
Team 3.
So let's get some whiteboard space for y'all so you can start working on this.
2. 1, right? Anyone talking to 2?
I think we gotta pull it out. Like,
pull it out.
It works. We're not using it. You guys
Okay, so anyway, keep in mind, you saw that scaffolding. That code is already written for you. So your method is going to be a class method inside the hash table class.
What? Your one?
Yeah.
I had a feeling.
Who's the one?
Oh, okay, so that's 4?
Brilliant.
Yeah.
Are you guys on? Yeah.
This is 1. Oh, over there.
Alright, I'm
Yeah, sure. We'll be closer to getting in there, too.